don't know why it takes 15 minutes to get the darn thing to work every time, but it does. Everybody should have gotten at least one email from me yesterday. If you did not get any emails at all from me yesterday, there's a problem. And you need to see me right after class. Anybody not get an email?
I didn't send my email address to you.
That would be a good reason why you wouldn't get an email.
I'll do that right after
Now,
class.
that's gonna cost you some effort now, because you're gonna have to read a bunch of emails that I haven't sent you. No one else, okay. So right now, everybody but you have access to the materials that I put in the Google Drive. And as of earlier this morning, my first 6 sets of lecture notes, that's not the first 6 lectures, but the first 6 sets of lecture notes, which will go at least 3 or 4 weeks, at least that, have been posted, all right? So dig in. And the syllabus and lecture notes I sent you as email attachments, but I put copies of them in the folder just in case you mislay the ones I sent by email. And keep in mind that the dates of the exams and that kind of stuff are already in the list of lectures, including the final exam. So that's there now. And if there's a problem with an exam, then please don't come to see me the day before. That just makes everybody's life difficult. But if there's a problem, see me, like a week ahead of time, and we'll do something about it. That's convenient for everybody, rather than a last-minute excitement. Okay, well, last time we started to talk about the process of extraction, and I posed this one example problem, that is the purification of compounds A and B, both initially present in some organic phase, and we want to see what we can do in terms of purifying these phases by extracting them with water. So this is some organic phase up here, and we're going to extract with water. Okay, so the initial concentrations in the organic phase are 1 millimolar each. And I assigned these partition coefficients, where I said these partition coefficients were the partition coefficients for the transfer from the organic phase into water. So that means both K factors correspond to the equilibrium concentration in water over the equilibrium concentration in the organic phase. And I said we're going to assume that we have 100 milliliters of the organic phase to begin with, and we're going to extract with, I mean, you can decide what you want to extract with, what volume you want to extract with, but I took 100 to keep life simple for everybody. Okay, so that's the volume of water that we're extracting with. So the K prime, or the retention factor, would be the K factor times the phase ratio, where in this case the phase ratio would correspond to the volume of water in the numerator divided by the volume of water, so I'm sorry, organic, in the denominator. That's the way we set this up the other day. In this case, since both volumes are equal, it doesn't matter what you do. But if they weren't equal, then you really have to get this phase ratio correctly. So in this case, then phi is going to be 1. So the two K factors then are K times 1 and K times 1. Here's the Ka. So K prime A is going to be 0.01 times 1 is 0.01. And K prime B is going to be 1 times 1, which is 1. The fraction of A, the mole fraction of A that goes into the water phase, or the mole fraction of either A or B going into the water phase, the X, the water phase is going to be K prime over 1 plus K prime. So in this case, for solute A, it's going to be 0.01 over 1 plus 0.01. And for the organic phase, it's going to be 1 minus that. The two mole fractions, right, the mole fraction in the water plus the mole fraction in the organic phase, those mole fractions have to add up to 1. There's no third phase. So they must add up to 1. So this has to be 1 minus the mole fraction in the water phase, and 1 minus K prime over 1 plus K prime is simply equal to 1 over 1 plus K prime. That's just algebra. So that's going to be 1 over 1.01. Something like 0.99. Now, I'm not going to bore you doing the B, because K prime is 1. So we have K prime over 1 plus K prime. 1 over 2 is a half. 1 minus a half is a half. So what happens here, looking at these numbers, is that very little of the A goes into the water phase. Very little. But half of the B goes into the water phase. So have we purified the A to any extent? Yes, because we've removed a lot of B here, up here. And then in the receiving phase, in the water phase, you haven't extracted very much A, but you've extracted half of the B. So the ratio of B to A down here in the water phase is pretty high. And you've removed a lot of B from here, half of it, and you've left most of the A up here. So you've improved the A to B ratio even in the starting phase. And you've almost doubled it because you've only taken out a little bit of the A and you took out half of the B. So in fact, you have produced some degree of purification. Clear? What if, and I'm being purely hypothetical, what if this number were not 0.01, but was equal to that number? Would I be able to effect any purification in either phase? No, because the ratio of A to B in both phases would be the same. In order to do an extraction purification or any phase equilibrium purification, be it gas chromatography, liquid chromatography, size exclusion chromatography, anything, you must have a difference in this thermodynamic quantity, this partition coefficient. You must have it. Does the phase ratio influence that conclusion? No. It doesn't matter what the phase ratio is. It's the difference in the K factor, the big K factors. That of B in the organic phase is going to be 0.5 millimolar. The equilibrium concentration of A I screwed this up. This is 0.99 millimolar, and this is 9.9 micromolar because it doesn't like the A. And we have 0.5 B in both, 0.5 B millimolar B in both phases. So we've done pretty good here. Now, just look for a moment at case 1. Case 1 is what I just described, where we've extracted the A and the B with 100 mLs in the water phase and 100 mLs in the organic phase. Initially, before we do anything, we have the same number of moles of A and B in the organic phase. So the ratio of B to A is 1 in the organic phase. In the organic phase, when we're done, the ratio of B to A is 50. That's a big improvement in the purity. We've extracted half of the B into the organic phase. So we haven't recovered all of the B. We've only recovered half of the B, but the B that we've recovered has been really rather highly purified. I mean, it's improved 50-fold. That's not bad for one step, but most of that, all of that, in fact, is due to the huge difference in those two partition coefficients. Now, I could do the extraction in case 2 in a different way. In case 2, what I'm going to do is I'm going to start with my 100 mLs of organic phase, and I'm going to extract not with 100 mLs of water, but with 200 mLs of water. Okay? So I'm changing the phase ratio, but I'm keeping the big K factors the same. Is there a change in the results? Yes, there is a change in the results. What you'll find now is that there's less A left in the organic phase because you increase the volume of water, which increases the K factor. The equilibrium concentration of the A in the water phase, it was 0.99 millimolar with 100 mLs, but if you use 200 mLs of water, it drops by a half. And things change also for the B, for the amounts of B. And if we look at the organic phase, the ratio of B to A in the organic phase has actually improved. But it has cost you something. This was the concentration of B in the organic phase with the 100 ml, 100 ml extraction. But with the 100 ml, 200 ml extraction, you do improve the purity, but the concentration of the B in the organic phase has gone down. This is a classic trade-off that you see time and time and time again in separation science. You trade yield for purity. You can't simultaneously, by just a simple volume manipulation, a simple geometrical manipulation, get both. There's got to be a price you pay. There has to be. There's no magic in separation science. Sometimes it might look like that, but there's no magic. You always have to pay some price. Sometimes that price is just money. Sometimes it's something important, like time. Okay, I want to propose a third way to do the separation, but it's a little more complicated. So here's what we're going to do. We start with 100 mLs of organic phase. We're going to extract it once with 100 mLs of water. It's going to bring it to equilibrium. Then we're going to remove the water phase, put it in a different beaker. We're going to add another 100 mLs of water. And we're going to do the extraction again. And then we're going to take that 100 mLs of water and put it in the beaker with the first 100 mLs of water. So in case 2 and in case 3, I'm using a total of 100 mLs of water to extract the stuff out of the organic solvent. That's the same. But in case 3, I'm doing more operations, I'm doing more work. The first extraction that I do of the pair is identical to case 1. So all I do is repeat the calculation of case 1 twice. Now the first time I did the extraction, I removed half of the B, right? And the second time I do the extraction, I'm going to remove half again. So basically all you're doing is squaring the mole fraction that you extract each time. So the fraction remaining in the initial phase, so that's the fraction, the mole fraction remaining and I just showed you that that's what happens if you do it twice. If you do it n times, you can show yourself that the fraction remaining is 1 over 1 plus k prime, the whole expression raised to the n power. Now, here's the really cool thing, if you get excited about stuff like this. Look at the purification factor now for B. That's big. So by doing the fancy two-step extraction, you really get a humongous improvement in your purification. However, the yield trade-off that I mentioned is still true. And when we're done combining those 200 mLs of water to get our final B, it's now even lower than the one-step extraction with the 200 mLs in one shot. So you still got a yield or concentration versus purity trade-off. It still happens, even though you did more work, more steps. You can't fool Mother Nature. You just, I should say, you can't fool entropy. This is fundamentally an entropy trade-off because this is more dilute and this is relatively more concentrated. You've got a balance in entropy of dilution against the entropy of your mixture. There's just no way around it. Okay, a few details. Let's suppose I do repeated extractions, 1, 2, 3, 4, 5 extractions, and my K prime is 1. Well, if you do 1 with a K prime of 1, then the fraction remaining is a half. If you do 2, it's a quarter, like I just showed you. If you do 3, it's an eighth. If you do 4, it's a 16th. If you do 5, it's a 32nd. If K prime is 3, that means more of the stuff extracts. There's less remaining on the first shot. 1 over 1 plus K prime is the fraction remaining. 1 over 1 plus 3 is 1 over 4. That's 1/4. That's where that number comes from. If we do that twice, it's a 16th, and so on. I I picked 9 in this case because I'm going to add 1 to it, and I can do 1 over 10, hundredth, thousandth, a 10,000th, and a 100,000th after 5 extractions. There's your fraction remaining. Okay, each time I'm doing the extraction identically. Is there another way to do the extraction? Yes, there is, because otherwise I wouldn't ask the question. In the repeated extractions, what I did is I kept adding more volume and more volume and more volume. So my total volume back here is 100 mLs, 200 mLs, 300 mLs, 400 mLs, 500 mLs. Suppose I want to do repeated extractions, but I want to keep the total volume of the liquid that I'm using to do the extraction constant. Let's say at 100 mLs. So if I'm only going to do 1 extraction, I use 100 mLs of the extracting fluid. If I do 2 extractions, I'm going to take 50 and 50. I wind up with 100. If I take 3 extractions, I'll take 33 and a third, 33 and a third, 33 and a third. Okay, so that's another way I could do that repeated extraction. Does it change things? Yes, it does. Whoop. So now, this is the fraction remaining. The fraction remaining is larger because each individual extraction removes less than if I use the total volume in one shot to do the extraction. So the results of the separation depend very much on the details of the separation, right? One last question I want to ask, and I have to get myself a new slide to write on here. That's going to be the final equation for the fraction remaining if I use keep the total volume constant. And K prime naught is the K prime factor for the first extraction. You've got to put in the correct volume that you're extracting with. If you take the limit of this as n goes to infinity, because, I mean, you have to see what you're gaining. The limit for the fraction remaining is exponential minus the equilibrium constant times the total volume of the extraction fluid divided by the volume of the organic phase. In other words, there's a natural limit to how many small increments of fluid you want to extract with. I mean, if you're down to extracting 100 mLs of stuff using 1 microliter of water, and you're going to do that then 100 mLs divided by 1 microliter, that's a lot of replicates. It's probably too much effort to try. It's a stupid thing to do anyway. But there's no point in trying to beat this limit because you can't do more than an infinite number of extractions. And what you'll find out is 4, 5, or 6 extractions are just a teeny tiny bit different than this number. So why bother doing 7 extractions? No point in it, right? But there's another message here. N is an integer. It can be 1, 2, 3, 4, 5. But the limit in behavior is a continuous function, not a discontinuous function. I just mention this because when we approach the plate model, we're going to get a discontinuous function. In fact, it's going to be a horrible discontinuous function with factorials in it and things raised to the integer powers and just, ugh. But turns out that in the limit of a lot of plates, it's a nice simple continuous function. It's the Gauss function. Someone wrote me an email the other day, I forget who, asking, well, how can this, how can you represent what goes on in a column with plates which are discontinuous devices, whereas the column's continuous? Because you take the limit of a large number of plates and it becomes continuous. It's just a mathematical trick, in other words. Okay, so back to the Kraig machine, and I briefly went over how it worked. I want to remind you about how the Kraig machine works. We number our tubes 0, 1, 2, and there can be a lot of these. We have an upper phase, which is immiscible with the lower phase. We move only the upper phase. We put the solute in to begin with, the solute mixture, if it's and there's no other reason to do this unless you've got a mixture. You put your solute in the 0th tube at the beginning. And you only put the solute in at the beginning. You don't add any more later. You shake up the 0th tube, you bring the 2 phases to equilibrium, and then you move only the solute that's in the upper phase over into the adjoining tube plate. And now you put in fresh mobile phase into the 0th tube. No solute. Now you got solute in both tubes. You shake them up, bring them to equilibrium. Then first you move this stuff over there. Then you move this stuff over here. Then you put fresh mobile phase in the 0th tube again. And so on and so on and so on. And eventually, the stuff that you put in here is going to march down the tube and get to the last tube, where you bleed out, where you take out that mobile phase that you're putting into that last tube. That's how the Kraig machine works. Now, if there's a difference in the big K factors for the 2 solutes A and B, you're going to get a separation. If there's no difference, you're not going to get a separation. Okay, so let's now work a Kraig machine, and we'll take the simplest case going. We're going to make believe that the phase ratios are the same. Okay, so we get the same amount of fluid in up top and bottom. We don't have to do it that way. You could take twice as much in the upper tube as you have in the lower tube, but it'd have to be the same in all the tubes. You don't mess around with it in the middle. You got to, once you start, everybody's the same. Okay? Now let's take the case of a K factor of 1 with a phase ratio of 1, which means that the little k, the retention factor, K prime, little k prime, is you've seen it 3 times already now. Big K is 1, phase ratio is 1. This is not a trick question. 1. So the fraction of the solute that's at equilibrium in this tube at equilibrium, the fraction, first extraction down here is what?
50-50.
it's 50-50. The fraction down there is a half, the fraction up there is a half. Okay, at equilibrium. Now we're going to take this. So now, the mole fraction of the solute in this upper phase at equilibrium, and mole fraction now refers to all of the moles in the whole system, not just in the zeroth tube. What's the fraction in this layer here, the upper layer?
75.
It went down to a half. Do you think it's going to come back up?
Are we counting both of them though?
We're counting the whole system, and I want the mole fraction here, 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 and there. Oh, before we do the second extraction, you have a mole fraction of a half there and a half there. You now transfer out the stuff up here over to here. So what's left in this tube? In the whole tube, what fraction of the material is left in the tube? Somewhere. Half. What fraction in the whole tube is in this tube? Okay, now, shake them. Equilibrium. What mole fraction is left up there?
Quarter.
A quarter. Down here?
A quarter.
Over here? Okay? So when we're done, at equilibrium, I've got half of everything here, I've got half of everything here. So I started with 1, now I have a half and a half. Now I'm going to do it again, but I'm going to take what's up here and put it over there. I'm going to take this, put it over here. I'm going to bring in fresh mobile phase, and now I'm going to shake the whole thing again, bring those 3 tubes to equilibrium. I'm going to have an eighth here, an eighth here. I'm really going to have 2/8 here and 2/8 here. And then I'm going to have an eighth here and an eighth here. So that's going to give me 2/8, also known as, what's 2/8?
Quarter.
Okay? And I can't do the rest in my head, but the next go around, numerically, book 2. The next go around is 1/8, 3/8, 3/8, 1/8. Now if you think back to your high school algebra, you'll recognize this as the binomial expansion. Of those 2 fractions. I think Bernoulli in the 15th century discovered the mathematics of these types of expansions. This is an easy one because the mole fraction was a half. But if your 2 fractions are represented as P plus Q, then you're going to be looking at the binomial expansion of not a half and a half, but of whatever fraction and whatever fraction. The P and the Q have to add up to 1. You can't just take any 2 fractions. They have to add up to 1. And you can generate then the binomial expansion of any system you want with any given retention factor, K prime factor. So here's where we start. There's the first extraction at equilibrium after the second, after the third, after the fourth, after the fifth. That's with K prime of 1. And we can plot this distribution. So here's a plot of the mole fraction. This is the mole fraction in the tube, not in the upper or the lower, but in a combined up and lower of a tube, versus this axis here is the tube number axis, and R is the number of transfers that we do. So at the 0th transfer, before we do any transfers, it's all in the first tube, and the mole fraction is 1. I'm sorry, this is with a K prime of 2. I went too far. Oh, there we go. Here's K prime 1. It's still the same answer for 0 transfers. It's all in the first tube. It's 1. If K prime is 1, and if we do the first transfer, it's a half and a half, a quarter, a half, a quarter, 1/8, 3/8, 3/8, 1/8, and so on. So what you see is the distribution shifts down the tubes as you do more and more transfers. And eventually, the whole distribution would move through the last tube. Now, we can do the same calculation with P plus Q, where P is a third and Q is 2/3, and do the binomial expansion of that, or you can just work the problem in your head. These numbers are not that difficult to deal with. With K prime at 2, Q, the stuff that stays in the tube, in the stationary phase, K prime 2, 2/3 is in the stationary phase, 1/3 is in the mobile phase. We start with 1. Then on the second transfer, more has got to be in the 0th tube than the first tube because the K prime is bigger. So this is bigger than that. So this peak is bigger than that peak. And we keep doing this, and you see after 4 transfers, in this system, in the K prime 2 system, the distribution is lagging behind the distribution in the system with the K prime equal to 1. So the stuff with the K prime of 1 is going to get to the last tube before the stuff with the K prime of 2. There's a separation. Now, this doesn't look like a great separation because the Kraig machine doesn't have that many plates. We've only occupied 4 plates. I've never seen a chromatographic column that had 4 plates. If you buy an even semi-decent HPLC column, 5 centimeters long, it's got at least 5,000 plates on it, or you send it back to the manufacturer. A decent capillary GC column that's, say, 20 meters long has got easily 15,000, 20,000 plates on it. So this doesn't really look that good yet, but the basic principle of the separation is here. So let me show you what the plot looks like now for more transfers using the binomial expansion formula. So this is what it looks like with K prime of 1 after 10 transfers versus tube number. Now, believe it or not, this red curve is the results of using a Gaussian function and using the correct mean and using the correct width of the peak. That's not a bad fit. And there's only 10 transfers, so we're really dealing only with 10 plates. If my K prime is a half, you see the peak has actually moved down further than if K prime is 1. Right? There's the peak. About 4.5. This is about maybe 7. So it's K prime. But it's still not a bad fit. Even though we only have 10 plates. Not a bad fit. So, you know, if I were to show you the results of 100 transfers with a 100 tube system, and then put a Gaussian to it, there's no way your eye could possibly see the difference between the curve and the points. I mean, you could see it on a computer printout, it'd be out in the 3rd or 4th decimal place, difference between them. Okay, now, let's get into the guts of the Kraig machine. In fact, you can write an equation for the mole fraction in a tube as a function of the retention factor, the tube number, and the number of transfers. And again, this comes from the binomial expansion. So you can actually put this in Excel and knock yourself out, plotting this and having fun with it. But don't put in an R or an N like 30, because 30 to the 30 factorial will overflow Excel's capability of dealing with big numbers. But if you take smaller numbers than 30 or 32, I forget which one overflows the Excel, you can really see what these things look like. And it's interesting to use different values of the retention factor. And you'll see just how much ratio of retention factors you need to get a decent separation. And that, of course, depends upon how many tubes you pick. Okay, now this equation, I mean, nobody likes it, and don't memorize it. It's just useful for seeing what's going on when you're when you've got something to do the calculations with you. But it clearly, based upon the plots I just showed you, what it's predicting is a distribution of the solute in the different tubes that depends upon how many transfers you do, and depends upon the K prime factor, the retention ratio, the retention factor. All of those change the fraction that's in a given tube. The two most important characteristics of a distribution are, A, its center of gravity, its center of mass, its average position in the set of tubes. And we can easily calculate that the average position, the center of gravity, the center of mass, whatever you want to call it, is simply the average. And for a discontinuous distribution, the average tube number is simply the sum of the mole fractions times the tube number that mole fraction is in, divided by the sum of all the mole fractions. Well, the sum of all the mole fractions conveniently is 1. And so this is the center of mass. And that center of mass moves that through the set of tubes as we do more and more and more transfers. So if we take this binomial expansion function, put it in here for x, and then do the summation over all the tubes, that will work out to be R times Q, where Q is the fraction in the upper phase, and R is the number of transfers. So if you don't do any transfers, R is 0. Doesn't matter what fraction you're dealing with, 0 times that fraction is 0. The center of mass, if you don't do any transfers, has got to be in the first tube, because everything's in the first tube. No ifs, ands, or buts about that. As you do more transfers, the center of mass shifts linearly, i.e. with the first power of the number of transfers. Yes?
What did you say Q was again? I just missed it.
It is the fraction in the upper phase, the mobile phase. And it works out to be 1 over 1 plus K prime. The other important characteristic of a distribution, besides where's its average, is how wide is it? In statistics, when we've got a distribution, we relate the width to the so-called standard deviation. Okay, well, in mathematics, we don't talk about standard deviations, we talk about variances. And a special Greek symbol is used to denote variances, and that's sigma squared, lowercase Greek sigma squared. Statisticians and chromatographers, especially our friends, the chemical engineers, refer to this as the second moment of the distribution about the mean. Not just the second moment, but the second moment of the distribution about the mean. That's why I put this prime on the m sub 2. And this can be calculated for a simple distribution this way. I should have told you that n bar I'm going to use to represent the center of gravity when I'm talking about tube numbers. And it works out that this is equal to R times P times Q.
Wait, so is n bar the tube number at which the center of gravity?
It is the tube where the center of gravity is located. And you know, in this distribution, there's the 0th tube, the 1th tube, the 2nd tube, the 3rd tube, and so n bar, it may not, because it's an average over the distribution, it may not work out to be exactly 3 or 2 or 1. It'll be, because the mass is not all located in one tube. It could be in the middle. Well, you've seen plots where it was the 2 points were equal height, the 1/8, 3/8, 3/8, 1/8. It's somewhere between the 2 3/8. So it's not going to work out to be an integer all the time. Okay, very important point. That's the first power. That's the first power. Okay? So the width, the sigma is really the width. Sigma squared is the variance, right? So the sigma is actually the square root of R times P, look, that's a Q, times P times Q. I know I'm a minute over, but I have to say this. This is really critically important. This is the width of the distribution. This is how wide the distribution is. It increases with the square root of R, the number of transfers. The position moves moves with the first power of R. This means that the tubes, the peak moves through the tubes, right? Because it's a square root dependence of the width on the number of transfers. This is why chromatography works. If the width of the distribution also increased with R, it would spread out just as fast as it moved. And it wouldn't matter whether you had 10 tubes or a billion tubes. At the end of the day, you'd be just as bad a mixture as at the beginning of the day. You can't do separations unless the stuff moves through space, moves apart faster than it gets wide. And because of this, we want a lot of plates, not a few plates. So this is like one of the most important physical reasons and mathematical reasons why chromatography works. Okay, we got to a really good stopping point.